Hey, it's Bridgette, and today I'm going to show you how to do some HSC maths. For both A and B of the given questions, I'm going to be doing 5. Let's go. The question wants you to find and determine the nature of stationary points. To do this, I'm going to be using the first derivative. You can use the second derivative to find stationary points and determine their nature, and sometimes it's easier to, but today I'm using the first derivative. The first derivative tells us about gradient. It gives us an equation for the gradient of whatever line you derive. For example, if you're going to derive this line, it'll give you the gradient, which would be 2. A stationary point is a point on any line where the gradient is equal to 0. On a function, this can look like this, that point there, this point here, this point here, this point here. All of these points are where the gradient would be equal to 0. This one is called a minimum, this one's called a maximum, and these are both called horizontal points of inflection. Through the equation of a gradient, we can determine what kind of stationary points they are without actually graphing out your function. If the gradient of the left-hand side of a point is positive and the gradient of the right-hand side is negative, we're looking at a maximum point. This is because here the gradient is positive, here the gradient is negative. It's the same for a minimum point. If the left-hand side is negative and the right-hand side is positive, you've got a minimum point. If the left-hand side and the right-hand side are both negative, or the left-hand side and the right-hand side are both positive, you've got a horizontal point of inflection. Once you've found your stationary points, whenever the function you've derived is equal to 0, by substituting in an x value either side of your stationary point, you're able to determine the concavity of your points. So my step 1 is finding the coordinates. So first step is going to be deriving our function. So now I want to make it equal to 0 because I want to find where the points are stationary. Remember, this is now an equation for the gradient of the function. To do that, I'm going to factorize out 12x because I want to make it a quadratic. That way it'll be easier for me to find the stationary points. We know that our sum is going to be 1 and our product is going to be -2. Positive 2 times -1 equals -2, and positive 2 minus 1 equals positive 1. So from this equation, we can determine that we're going to have stationary points, or points where x equals 0, at -2, positive 1, and 0. Alright, I found the x values of all of these points, but I still need to find the y values. So what I'm going to do is I'm going to substitute these x values into the original equation, and therefore determine what y equals. -32. When x is -2, y is -32. Now we're going to repeat that process for the other 2 points. Figure out 0 plus 0 is minus 0 is 0. Alright, now we have our stationary points, but we need to determine their nature. I'm going to test a point either side of the x values of these points and determine their nature. I'm going to be using -2.1 and -1.9 for the x value of -2. Remember, of course, that we are using the first derivative for this, because this is about the gradient, because we're trying to find the concavity. Now, because I've tested a point either side of it, I can determine that the gradient on the left-hand side of the x value -2 is negative, and on the right-hand side it's positive. Or if you want that visually, if this is the point -2, when it's on the left-hand side, the gradient's going to be negative. It's going to hit 2, and that's our stationary point. And then on the right-hand side, it's going to be positive. Therefore, -2, 32. Oh my gosh, -32 is a minimum. Right, now I'm going to repeat that process for this value and this value. Alright, so I've determined that the point -2, -32 is stationary and it's a minimum point. The point 1, negative 5 is a minimum point and it's stationary, and the point 0, 0 is a stationary point that is a maximum. So we're on to 5i, and this time we're going to be graphing the function. I haven't yet removed these because we're going to need them for this. I need a ruler. I'm definitely not going to do this to scale. First things first, I'm going to draw out y-axis, x-axis. First stationary point, easiest one to do, 0, 0. Our next stationary point, 1 on the x-axis, negative 5 on the y-axis. That looks about right. And now we've got negative 2 on the x-axis, so 2 about there, and then negative 32 on the y-axis, so I'm going right down here. This is going to be our point, negative 2, negative 32. Now I'm going to graph my function. So we know that this is a minimum value, it's going to be increasing on the right hand side and decreasing on the left hand side. That's the easiest way for me to do it. Alright, and we're going to do our arrows because functions are indefinite. But what you can see here is I've got my stationary points, and these are the points where the gradient equals 0. Negative 2, negative 32 is a minimum point. 1, negative 5 is also a minimum point. And 0 is a maximum point. Easy question, easy marks. Embarrassing if I got it wrong though, lol. Alright, so we've made a error. When I graphed out my function the first time, I didn't include intercepts. X-intercept, you make y 0. So here is our function. I'm going to factor out x squared. I'm going to make it equal to 0 because we're trying to find our x-intercepts, so you make y equal to 0. Now I'm going to turn this into a quadratic. So I can't actually, that's not a real number. So I'm going to be putting it into the quadratic formula. Quadratic formula. Get out your Casio and solve that. Well then, oh. So x could equal 1.44 ... negative 2.77 ... X-intercepts. Y-intercepts make x equal 0. It's 0. Alright. 5i. For what values of x is the function increasing? I've left this up here, and I'm also going to do a little drawing of the graph to help me. This is only worth 1 marks, and while I am going to work it out mathematically, I'm also going to be looking at the function, and that's going to help me. This is another question that's based on gradient. I've drawn out another little graph of the function here because that's going to help me. Since this is focused on gradient, you can already guess I'm going to take the first derivative. Whenever the function's increasing, it's going to be positive values. Does everyone get that? Why am I asking? No one's listening. When the function's increasing, it means it's going to be having a positive gradient. Because if you look at this, this is where the function's decreasing, here's where the function's increasing. So I want to find the area on this graph where the x value has a positive gradient. To do that, I'm going to go. Of course, we can simplify this out like we did earlier. Oh my god. Alright, so there's only one problem that I have with these results. And that is because I know from here that when x is greater than 0, from the points from 0 to 1, the function is actually decreasing. So, I'm going to word this like this. When x is greater than negative 2, but less than 0, the function is increasing. And when x is greater than 1, function is increasing. Done. For what values of k will function x equals 3x to the power of 4 plus 4x to the power of 3 minus 12x squared plus k have no solutions? Add a number to an equation in the way that k has been added. It's going to raise or lower the whole function on the x-axis depending on whether the number is positive or negative. If we're going to graph y equals 2, here's the point 2, that's how that function is going to look. We can all agree on that. It's a line. When it's y equals 2 plus 2, that becomes y equals 4. and in turn, our whole function is going to be raised by 2 units. That's a really terrible drawing. So, this function is going to have no solutions when there is no x-intercept. When this function no longer hits the x-axis, that means that there is going to be no solutions. This is a really rough drawing, but we can determine that this is the lowest point on the graph. So for there to be no x-intercepts, we're going to have to raise this graph by more than 32. Because if you add 32 onto it, it's going to raise it until it hits the x-axis, and there's still going to be an x-intercept. So our answer for this, k has to be greater than 32. If k is greater than 32, that is going to lift our function above the x-axis, and therefore there's going to be no x-intercepts and no solutions. And with that, part A is done. Alright, so the second question focuses on geometric applications of calculus. This combines geometry, which we did earlier in the year, with things like differentiation, minimum and maximum points, etc. John's home is at point A and his school is at point B. A straight river runs nearby. The point on the river closest to A is point C, which is 5 kilometers from A. The point on the river closest to B is point D, which is 7 kilometers from B. The distance from C to D is 9 kilometers. To get some exercise, John cycles to E before cycling to B. Oh my god, itchy leg. First question. Question 5I is, the total distance John cycles from home to school is L kilometers. Show that L equals the square root of x squared plus 25 plus the square root of 49 bracket 9 minus x bracket squared. Mathematically, the distance L can be described as AE plus BE. We aren't given those particular distances. What we do know is that these are both right-angled triangles, but we are given the distances of AC, CE, ED, and BD. And we know what this means. Old mate Pythagoras is joining the party. Pythagoras' theorem, the hypotenuse squared equals one of the other sides squared plus the other side squared, or a squared plus b squared equals c squared. According to Pythagoras, AE squared should equal CE squared plus AC squared. AE squared is equal to 5 squared plus x squared, which means that AE will equal 25 plus x squared. So now to simplify this, I'm going to take the square root of AE. Alright, so now we have our length AE. We're going to find our length BE. BE squared equals 7 squared for this side. So we aren't actually given a distance for DE, but we are given the distance from D to C, which is 9 kilometers. The only thing that separates DE and DC is x. So my distance for DE is going to be, in brackets, 9 minus x. And then we're going to have to square it because that's Pythagoras. Taking the square root of BE, and now we have the lengths AE and BE, which plus together are going to equal L, which is the distance we're trying to find. Our distance L is going to be our distances AE and BE put together. This is looking pretty close to this. We've just got to add them together. L equals... This is addition, so it doesn't actually matter what order you have them in, as long as they're both getting plus together. And in this equation, they're the other way around, so I'm just going to flip them. So that's our distance AE, and we're going to add it to our distance BE, which is... There we go, first question's done. For question II, show that if dl over dx equals 0, then sine alpha equals sine beta. Here's a less detailed version of the diagram, because I just wanted to point out that this is the angle alpha, this is the angle beta. If the differentiated version of L equals 0, then these two angles are going to be equal. First thing we're going to do for this is differentiate L. We figured out L in the last question. Rewrite this equation so that these square root signs are written as this to the power of a half, because we've got to have powers so that we can differentiate. So L equals, in brackets, x squared plus 25 to the power of a half plus bracket 49. What did I write there? So here's our new version of L that's a bit easier to differentiate. I'm going to differentiate this and this separately because that's just going to be easier for me. So I'm going to call this new equation A. The differentiation of A equals half x squared plus 25 to the power of a negative half. And since this has brackets in it, we're going to apply chain rule. You multiply your differentiation by the differentiation of what's inside your brackets times the differentiation of this, which will be 2x. Times 2 cancels out, and that's going to become alright, and now we're going to differentiate the other half of the equation, which I'm calling B. This one's chain rule again, except chain rule is going to apply twice because we've got two sets of brackets. I'm going to multiply this, 2 bracket 9 minus x, and then multiply it again by negative 1 because we have to multiply this bad boy. Don't forget your negatives! I'm going to simplify this down now. This 2 here is going to cancel out the half here, and this negative 1, I'm just going to apply that to that and chuck this out the front. Negative 9 minus x, bracket 49 plus bracket 9 minus x squared to the power of a negative half. L dash is going to equal A dash plus B dash, so what I'm going to do is write that out in a chunky equation. So here we've got our L dash. Alright, so now I'm going to rearrange these so that they're back in their original form. So I'm putting x on top, and then over the square root of x squared plus 25. This negative here is put there. What I've done here is I've just put it back into its original form. And because in our question it wants us to make it equal to 0, that's what I'm going to do. Now I'm going to figure out what sine alpha and sine beta are. So we all know, thanks to Sokotoa, that sine is opposite over hypotenuse. So I'm just going to box this off for a second because we're going to come back to that later. Now I'm going to find sine alpha and sine beta. We know that sine is equal to opposite over hypotenuse. So for this question, sine is going to equal the opposite, which is x, over the square root of x squared plus 25. Similarly, we're going to work this out for beta. I'm just going to write in sine alpha there. For sine beta, it equals 9 minus x over the square root of 49 plus 9 minus x squared. You will notice that sine alpha looks identical to this part of L dash, and sine beta looks identical to this part of L dash. So the question is asking us, if this is equal to 0, show that sine alpha is going to equal sine beta. The reason that the negative was so important is because algebraically we can move this over to this and change the sign. Then, from these we can determine that when L dash is equal to 0, if that equation is rearranged, it shows that sine A is equal to sine B. Question III of 5 is find the value of x that makes sine alpha equal sine beta. I've written up the sine alpha and the sine beta equations, and I'm going to work on isolating x in this. Get rid of the square root signs, and to do that I'm going to square everything. Now I'm going to expand, and now that I've got this, I'm going to cross multiply. I'm just going to move this up to the top. Now I'm going to expand out these brackets. I'm just going to take this down a line. So this is the left-hand side of my equation, and this is the right-hand side of my equation, and I'm going to group like terms. So from here, I can tell that some of these terms are going to cancel out. I've got negative 18x to the power of 3 on both sides, and I've got x to the power of 4 on both sides. When you minus 1 off this side, you minus it off this side, and when you add 18x to the power of 3 on this side, you add 18x to the power of 3 on this side. So they both have to rack off. I'm going to move everything from the right-hand side onto the left-hand side. X squared plus 450x minus 2025. And that's going to equal 0. Moved everything over. The best part about this is that we've now got a quadratic. Here's our quadratic formula again, and I'm just going to substitute my A, B, and C values into that formula. Now that I've copied out my quadratic formula, it's going in the calculator. First x value is equal to 15 over 4. And our second x value is negative 45 over 2. So while both of these x values would make it so that sine alpha is equal to sine beta with the original formula, the original question is talking about distances, and distances can't have a negative value. So since we have these two, we're led to believe that 15 over 4 is our only applicable answer. IV, explain why this value of x gives a minimum for L. We're aware from the first question that in order to have a minimum, the left-hand side of your x value needs to be negative and the right-hand side of your x value needs to be positive when you sub it into the differentiation of your equation. So that's exactly what we're going to do with our x value from the last question, which is, of course, first thing I'm going to write out L dash. Now I'm going to substitute in a point either side of my x value, and that's going to explain why this is a minimum value for L. My left-hand side of 15 over 4, I'm going to do the function of 14 over 4. Chuck it into your calculator. Negative 0.04435 for the left-hand side. Now I'm going to substitute in a value on the right-hand side. That I'm doing 16 over 4. And we all know that 16 over 4 is just 4 for my x value. 0.04, and that's for the right hand side. So when we initially did minimum maximum values, remember that when it's decreasing on the left hand side and increasing on the right hand side, we have a minimum value. And as you can see, when our x value is 15 over 4, if we test a point on the left hand side, it comes out as a negative value, and test a point on the right hand side and it comes out as a positive value. This value of x gives a minimum for L. Maths is done.